guys, we need to cover UV viz today. Before we do that, though, we'll do a little miscellaneous catch-up, etc. Including, if you have any questions about substitution, elimination, anything for the test. Test is a week from today, yeah. Format is the same as the first two tests. Let's see, we have nomenclature of dienes. Then we'll have some multiple choice questions. Line reactions as usual, or we have line reactions on test 2. Line reactions consist of mainly like predicting product. It could also be give a reagent, or it could be what is the starting material that would be used to give this product, etc. Mechanisms, using arrows to show all electron movement. So the mechanism questions, and then the short answer questions. There's a couple of quizzes. There's also, some of you saw a quiz during SI today. We will have mass spec. Mass spec will be either, well, somewhat like in the workbook. There's a couple of variations. Some of the problems in the workbook was just assign structure to spectrum. There was one or two in the workbook where you did not have a formula, I believe. There was IR given with it. Question?
Yes. Could you possibly work out the one or the one with the mass spec where you had to just totally come up with the structure?
Not sure I brought my workbook. Which page is
You
that?
can use mine. I'm just trying to find it.
I keep forgetting to bring my notebook every day.
What's the name?
Okay.
We did that in here, I believe. Did we do nomenclature of dienes in here?
Yeah.
Pretty sure we did. Page 42 in the workbook. Determine the structure of the compound whose IR and mass spec are shown below. Look first at the IR. So you have correctly interpreted this very strong peak here about 1700 as a carbonyl. Yep, classical carbonyl. Peaks here just below 3000, sp3ch. There's a little blip over here. It's potentially an overtone. But mainly I see carbonyl, and this looks saturated. This seems to be an aldehyde. Carbonyl is 1710 or so. That's kind of a standard carbonyl. Let's see what we have down here. Molecular ion is, I don't know if that's something at 100. It's hard to tell. I see something at 86, and this looks like maybe a C13 isotope. So that's potentially the molecular ion of 86. If it's not, we're going to have a lot more difficulty. So I'm going to say that's the molecular ion for now, 86. So a compound has a molecular weight of 86, and it's got a carbonyl, and looks mainly saturated. We see main cleavage peak here, 43, that's the base peak, 43, so cleaved right in half. If it's got a carbonyl, which IR says it does, how do we expect that to cleave? Cleave to give a structure, what's the name of this structure that's formed in the mass spec from a carbonyl? Alpha cleavage, it gives, what's the ion called? Anybody? Acylium ion? So it looks like if all this is pretty standard, if it's not standard, we're going to have a difficult time. first off, we want to say, okay, standard cleavage for carbonyl. Because if you hear hoofs, you want to think horses first, not zebras or any other wild, crazy things. Let's think horses in this 43. Carbonyl with 43, a psyllium ion, that's this, with, how many more carbons do I need? That's 2, that's 24 and 16. That's 40. 3 H's, that right there's 43, right? I mean, there's an acylium ion of 43. Now, if we want to complete this and add 43 more to get 86, what else do we add here? I mean, what was... Any more, what else do we need here? Another 43, so... I mean, that right there is 15. What is that? 29? What's the molecular weight of this? C1, 2, 3, 4, C5, H something, O, 1 degree of unsaturation, it would be how many H's? 10. It would be 10, right? What does this add up to? 5 times 12 is 60. 86? If this was the structure, where would we expect it to possibly cleave? Right here to give that plus what? Plus that radical? So this is 86. We expect a mass spec with 43. We've got a mass spec with 43. What's this going to look like in the IR? It's going to look like that IR. It's got a carbonyl and saturated sp3ch. I'm proposing that's the answer. Does anybody have an alternative proposal for the answer? Do you see any other peaks or something that makes you think of something else? Actually, the answer is possibly yes. Anybody got another suggestion?
Could the
Yep.
could the other carbon be on the other end? Carbon be on the other end?
Could which carbon be on the other?
The single methane.
Methyl?
Could that be on methyl? Could that be on the other end?
You mean
Yes.
that? If it was there, this is also C5H10O, but what's here?
H.
H. So you're saying it could be an aldehyde? Does the IR look like an aldehyde?
I work in
IR doesn't look like an aldehyde to me. What am I looking at? The aldehyde CH, where does this get peaks at? 2750, 2850. It's just not low enough at there. You need to look. In fact, when I told you about this, I said you guys usually forget that. Look back. It doesn't look like an aldehyde. Anybody ever another structure it could possibly be?
Could that methyl be attached to the oxygen?
Well, if it's a carbonyl, how could the oxygen of a carbonyl doesn't have anything attached to it? And the IR looks like the carbonyl, right? I mean, you can't have an oxygen double bonded and the methyl on it. It would be charged. It'd be a very unusual compound. Is there done something else?
The chromium could be isotope.
Yes, that's what I was thinking. What if it was instead that there? Isn't that the same struct formula? That's a constitutional isomer. It's 86. Cleave here to get a psyllium plus an isopropyl radical, but that doesn't show up anyway. You still get the 43. IRVs you can't tell apart unless you're comparing a fingerprint. Saturated carbonyl. How can we tell these two apart? How can we tell these two apart based on?
The one with the purple, they could be these case of cleavage of another one of the isopropyl, they would be.
This can undergo what type of cleavage? It has an alpha, beta, gamma carbon with gamma hydrogens. It can undergo McLafferty, which is essentially going to cleave here to give this, or you can show the carbonyl form. That's keto. That's the enol form. This is going to lose ethylene, which is going to be 2 carbons and 4 H's. 24 and 4, 28. Minus 28. What is that? 86 minus 28 is 56, 50, 58? Is it 58? You already got it right there. I do see some 58. So you don't expect that one to lose 58 McLafferty. That's more evidence that it's indeed, this is the answer. How we doing? Is that the answer in the back? Hopefully it is. Looks like it to me. Any questions about that?
Yeah, that's.
This is up here. We need to learn this flow chart. Make sure we know this. We're ready for this for the test. Need to send this out. This is a flow chart. Huh? What does it say? This is a flow chart for predicting substitution or elimination reactions in either SN1, SN2, whatever. First question, is there an sp3 carbon with a leaving group? If there is, well, congratulations, you can do substitution elimination reactions. Yes, that means all these are possible. If there is no sp3 carbon with a leaving group, guess what? You can't do them. But we already know that, right? Haven't we already said that a couple times? So step 1 we already knew. Okay, next question you can ask, is there a beta hydrogen? Because if there's no beta hydrogen, guess what? You ain't doing elimination. So we already know that, right? And if you ain't doing elimination, it skips you down to 5A. Well, if there is a beta hydrogen, well, guess what? They're all still possible. Because just because a compound has a beta hydrogen doesn't mean you're going to do elimination. You still do substitution. Right? Then you say, is the beta hydrogen coplanar with leaving group? Now, some of these, this is not my here, I would sort of modify some of these. I would say, can the beta hydrogen be coplanar? Because it may not be as strong, but we can rotate it. Basically, things like this to exist,
I have a question, I'm a little bit confused.
Uh-huh.
Because we're talking about individual carbons here, so we're only talking about the bonds that can rotate. So if there is a beta hydrogen, then doesn't it say the same thing as it can be at some point, as long as you twist it in the right conformation?
Right. Well, I'm not quite sure what you're getting at. I would just say, can the beta hydrogen be coplanar? Because I could draw it with it not being coplanar, but we could rotate it so it's coplanar.
Yeah, so is there ever going to be a time that there's a yes to it being there, but a no to it being coplanar? Possible being coplanar?
There actually are some. I don't think we ever looked at any, but you get into advanced structures, you could get one. We haven't done it though. You could probably get one where it just cannot rotate and become. The ones we did, we always rotated it and said, here it is now. But there are some structures where, due to lack of rotation or something, where it just can't achieve the coplanar, either syn or anti. If you can't achieve either one, then you can't do it at all. Of course, I hesitate to say you can't do it all because it may be closely achieved. But we have to be sort of cut and dry. Okay. Let's see what else it says here. Is there a very strong base? You know, some of this, it says very strong versus strong. See, I didn't separate very strong versus strong. It's saying if it's very strong, it's only going to do E2. Well, I didn't really say that. If it's strong, well, it's saying E2 or SN2. Does this make sense? Because if it's strong, didn't I tell you it's going to be bimolecular? So they're saying it's either one of your bimoleculars. So you see, I wouldn't really include, I didn't say anything like that. Now let's go down here. Is base or substrate crowded? If the answer is yes, which one's it going to prefer here? It's going to start preferring E2 more. Well, then if your answer is yes, what do you get to? E2. What if no? Well, it's saying they compete. And you start getting into that gray area. Let's look over here. What if these structure of substrate? If the leaving group is on a tertiary carbon, what do you think you're going to be doing? Are you going to be doing SN2? No, you don't do SN2 on tertiary. And it already eliminated E2 because, for a reason. So you're doing either SN1 or E1. We already knew that, right? Then it takes you to solvents. I sort of talked about solvents. And I showed you a reaction. I said it hexane. And when we said hexane, what do we say about that? We said no reaction if you look back. See, no reaction. But if you do it in a product solvent, which will promote formation of these ions, then it's possible. And when they're both possible, what do we say about heat? If you heat it, which one is that favor? Okay? There's a couple of things on here that I didn't talk about, and I probably will. Maybe I don't slightly agree. I'll send this out by email. One thing I hate about this is, first off, if I'd given you this at the beginning, you kind of maybe get a little bit like, wow, so what there? And you also have a tendency to maybe start trying to memorize this stuff. I give it to you now, sort of, hopefully, so you can confirm what you know. Okay? If you see something that's confusing, it may be where you didn't really cover it, or maybe it's something you really need to go back and look and figure out why. I'll send this to you by email. Don't let it confuse you, but do try to use it as a review and maybe learn something. Okay? Fair enough? What we looked at already, does it, you seem okay with it? All these arrows, when I first showed it, it was a little bit intimidating, yeah? okay? But it's not. We've done most of it. So I'll send that by email, hopefully sooner than later. Let's look at UV Viz. Any last questions about test material? Questions?
Why did they eliminate YouTube from the possible?
Where did they eliminate it at? There's no E2 here.
Right.
Well, because what does E2 require? Strong base. They gave you very strong or strong. See, they separated it into two different. I would have just said strong. If you got a strong base, you can do E2. What if you don't have a strong base? Can you do E2? No. That's why E2 is not listed over here. But see, neither means you don't have either a very strong or strong base. This means no strong base. E2 requires a strong base. First off, it's 2, which means bimolecular. To do a bimolecular, you got to have strong. And in E2 is the thing acting as a base or a nucleophile. It's taking an H, so you call it a base. So by default, you thus need a strong base to do E2. So strong base would be going this way or that way. This way means no strong base, so you can't do E2. That's why E2 is eliminated. Make sense? Other questions about Diene, Gilles-Alder, mass spec? What else we got? 1.2, 1.4 addition, substitution, elimination. On Tuesday, we'll have a group, at least one over here in the next door room. Who has not taken the test over next door? Which lab?
D.
D? Is that Dr. Miel?
Yeah.
Okay, that's a big, we'll do section D next door. Who else is not taken next door? What lab are you in? Elephant?
Yes.
What is that? Who's that instructor? On Wednesday?
Yeah.
Okay. That's a smaller group, right? We could probably also do that, because I think that'll fit. We'll have more room in here. We'll definitely do D, and hopefully E will also fit. So D and E, D is in David, E is in elephant, will be in the room next door, this smaller room with the chalkboard, to take the test on Tuesday, week from today. Everybody else will be in here? Okay. Other questions? Feeling okay about this material? Okay. Let's look at UV Viz. Good? Looks familiar? Well, when you do spectroscopy, you're usually using one of these here. Infrared. Remember back when you didn't know much about infrared? UV Viz. Well, ultraviolet, and between then visible, then infrared. Ultraviolet and visible is a combined spectroscopy called UV Viz. Okay? Of course, the visible is our colors, and they range from blue to red. Which is higher in energy, blue or red? Blue, because this is the higher energy in, gamma rays, X-rays, ultraviolet. The high energy ultraviolet from the sun can be most damaging. When you move into the visible, what's after ultraviolet? Or what do you hit first? Actually violet, which is almost blue. Violet, blue, and then you go across with, what are these colors? You start over here. Red is the weakest in energy. What's after red? No, this one. Infrared. But as you go this way, red, what is here? Orange, yellow, green, blue. Okay, so blue is more like here. Okay. Violet, what's after violet?
Ultraviolet.
Ultraviolet, okay. So in infrared, what are the units we use? On infrared spectrum. Reciprocal centimeters are called a wave number. Okay? It's reciprocal centimeter. Centimeter refers to wavelength. It's in centimeters, but it's reciprocal. Okay? What's typical wavelength of IR? Well, it's the anti-reciprocal of maybe carbonyls at what, 1700? Well, turn that into wavelength in centimeters, you would do reciprocal of 1700 to get back to wavelength. Isn't that right? Reciprocal is the original. I think I don't know math that well. So what's 1 over 1700? It's going to be something pretty small, right? Maybe 10 to the negative 6 or 10 to the negative 4. What is 1 over 1700? Somebody got a calculator? 17 times 10 to the negative 4. There we go. That makes it easier. So you see it's 10 to the negative 4. Plus you start getting higher than that, like 17. So that's infrared in terms of, but hold on. This is also meters, I believe. Did it say meters? That number would be centimeters, so you didn't have to turn it into meters to get to this range. All right? Basically, what are the sort of the wavelengths of UV? This is meters, so it's like 10 to the minus 8. What is 10 to the minus 9 also known as? 10 to the minus 9 meters is a nanometer. So this is like 1 nanometer. That would be how many nanometers? 10 nanometers. Okay? And this, and minus 7 would be how many nanometers? 100 nanometers. 100 nanometers gets you in here. That would be how many nanometers? Yeah, once you get 1,000, you're beyond. That tells us it's somewhere between 100 and 1,000 nanometers. Okay? Basically, I hope you just are able to kind of work your math and know your units, et cetera, et cetera. Let's see what else is on this page. And in UV Viz, we will actually plot actual nanometers. Not reciprocal. Not centimeters, but actually nanometers. And it'll be like whole number. So nanometers are used in UV Viz. Here's your visible nanometers. It's about 400 to 800, roughly. This is a little bit broader. Of course, wavelength, frequency, etc. Okay, let's look at this. First thing you see is a carrot, and you also see a UV Viz. It's about the same size as the IRs we have upstairs. Okay, you're going to put a compound there, and you're going to shine light through it. Very similar setup as IRs. Why the carrot? Because we'll eventually ask why is the carrot orange? Because of its absorption. What type of light is it absorbing?
Shorter wavelength.
Everything, but it's absorbing visible light. Okay, down below, we see an example of a UV vis spectrum. The peaks, what happened to the board? Absorbance comes from the bottom. Okay, there's no absorbance here. The absorbance is, boom, here. Where IR, typically your absorbance comes from the top. Okay? Or transmittance, whatever. We have wavelength here in nanometers, and then we have some type of absorbance. This can be of various units. It really doesn't matter what they actually are. Basically, you scan the region. This is being scanned from 200. You can scan way out to maybe 800. But for this particular compound, there's no absorbance out here. Your main absorbance is right here at about 200 to 240. It's cut off here. Why is it cut off at 200? We'll eventually say this, but most of your common entry model UV vis start at sort of at 200. Below 200, like at 100, that's called the vacuum UV. And if you want to do an absorbance, you have to do it under vacuum. Makes it more difficult, and so it's not as common. Why do you have to do it under vacuum? What are you removing with the vacuum? Air. What's in air? The main component. Well, not the main component, the main one for our bodies. Oxygen. Oxygen absorbs ultraviolet very heavily in the 100 range. You'll get a lot of absorbance here, but it's not from your compounds, from oxygen. Now, if you want to only see compound, you got to do it under vacuum and get rid of the oxygen. That's not commonly done, and so usually we just say, oh, let's forget about all that absorbance by oxygen. So that's probably why it's cut off there. What we see here is the main absorbance. It's called lambda max. It's the wavelength of maximum absorbance. For this compound, which is, hey, that's one of our dienes, right? 1,3-butadiene. The maximum absorbance is right here, which is, boom, what is that? 217? 217 nanometers, maximum absorbance. And then it tails off. That maximum absorbance becomes a physical constant, like a melting point or boiling point or something. It's a piece of data that can be given for butadiene. Okay. Now, UV vis is you're not going to get a lot of peaks like IR. Pretty nondescript compared to IR. This is the main piece of data you get. 217 is in the UV range. Okay. If we go back, we should have went across. But this was really on the front page. The UV range is like 200 to 400 nanometers. Visible is like then a little bit higher. Longer wavelength, right? Lower energy, longer wavelength, 400 to 800 is visible. Does it say vacuum UV somewhere? Oh, let's send that. It must say it on another page. But below 200 is called vacuum UV. Okay. So if we look at butadiene, one thing we can say about this is, now I'm assuming they just cut this off because there's just no absorbance out here into the visible. Butadiene is a colorless liquid. Why is it colorless? It doesn't absorb any visible. Okay, that's why it's flat out through here. To be colored, like that wall or that sweatshirt, the molecules have to be absorbing visible light. Okay. It's colorless. Lambda max is 217 UV. There's no absorbance in the visible. Okay, let's look at this one here. What's going on when the compound absorbs UV visible light? Okay. Go back to IR. What's going on when a compound absorbs IR? Bonds are sitting there stretching. Here comes the IR. Throw me some IR. Oh, the bond caught it, kind of caught it. Okay, there's a physical mechanism there, and it goes to a higher vibration. Okay, exciting the vibration. What's going on with UV vis? Throw me some UV vis. First off, here's the bond. Throw me some UV vis. I'm not interested in it. The bond is not interested in UV vis. Okay? It's only interested in IR. Okay? Because you got to match the frequency. What's going on here? The electrons get excited to higher energy levels. Okay? Now with bonds, those are made of electrons, but the electrons aren't said to be exciting to higher energy levels. You go to just a higher vibrational level. That's a weaker energy phenomenon. Here we go to a higher energy level, electron energy level. This can be shown with different electron excitations. We have these different levels. To get to this point, you have to do some really consider molecular orbitals. N refers to non-bonding electrons. Star means an excited orbital. N to pi star, what is that, pi to pi star, N to sigma star. Pi would come from like pi electrons, pi bonds, sigma bonds. Which electrons are more stable? Electrons in sigma bonds or pi bonds? Sigma. Sigma. That's why your sigma is lower energy. Because of that, they're harder to excite. And you see in going from here to maybe there, that's a long transition, meaning lots of energy. What's the easiest to excite on here? Right there. The easiest electrons to excite are your lone pair electrons, your non-bonding electrons. Those are easiest to excite. Each one of these types of transitions require a certain amount of energy. Some of your higher energy transitions, such as this to here, takes a lot of energy to do that. That's down below 200 vacuum UV. The ones we'll see in the regular UV are your lower energy transitions. And those are mainly these first two. Longer wavelength, meaning lower energy. Your pi to pi star is typically most intense and thus usually most important. We'll say more about it. Here's another actual spectrum. And somebody has, first off, there's sort of two maximum absorbances. It's sort of like a maximum here, which is what? About 240. Maximum absorbance, 240. That's been ascribed to a pi to pi star. But then you also have this sort of little blip. It's like there was some maximum absorbance here for some reason. It wasn't your global maximum. It's called kind of a local maximum. That's been ascribed to the N to pi star, because we do have non-bonding electrons. And where those were excited. These are easier to excite, so it took less energy. Longer wavelength, less energy. As we said, pi to pi star is usually the most intense. And your lambda max is often from your pi to pi star transition. So this compound here is absorbing in the UV. You get to 400, it's probably a flat line. It's probably no absorbance in the visible. The compound's probably colorless. On the other hand, let's look at beta carotene. Where do we see beta carotene at? In a carrot, okay? There's the structure of beta carotene. Here's the UV vis. What's the lambda max here? Right there? What is that? 440. 440. So this has moved to the right a good bit. 440 is actually in what region? Visible. Its main absorbance is in the visible. And if you absorb visible light, you're going to be colored. Question though, why is lambda max shifted towards longer wavelength? What does that tell you about the ease? Now again, this is probably from the pi to pi star transition. The fact that it's shifted to the longer wavelength, what does that tell you about the ease of doing this? Is it easier or more difficult? It's easier, and thus it's taking lower energy light. Why is it easier? That's why. Why does the amount of pi bonds make it easier? Conjugation. Why does conjugation make it easier? Let's look at that. We can start by looking at here. There's another slide that also shows this. Ethane. That's just simply, is the structure there? There you go, ethene. 2 carbon, alkene. Ethene, pi to pi star, starting here. Butadiene would be, now we have conjugation. 2 double bonds conjugated. What does this do? It makes the gap between your, now these down here are usually occupied with electrons. Okay, this is sort of molecular orbital. We haven't done any of that this semester. Everything we've been doing has been valence bonding. But you did see molecular orbitals in Gen Chem. These down here are occupied. So these would be electrons. And this is the pi, sort of the pi electrons here, because they're going to be the highest energy in this molecule. What do you want to call this level? It's sort of the highest one that is occupied with electrons. What do you want to call that level? No, those would be excited. Those are your higher energy. It's the highest occupied molecular orbital. What do you want to call it? Oh, y'all don't know? I just told you. Y'all don't know that term? HOMO, right? Y'all haven't heard HOMO? Highest occupied molecular orbital? Y'all don't know HOMO? Y'all didn't do HOMO and LUMO in Gen Chem? No. Okay. Now this one is unoccupied. What do you want to call it? It's also the lowest one. Somebody knows it. LUMO. That's the highest occupied molecular orbital. This is the lowest unoccupied molecular orbital. Okay. As your conjugation increases, the gap between your HOMO and LUMO decreases. Since it decreases, the energy you need to excite it here, I mean that's the arrow, it's like excite one up there. Do you need more energy or less to excite it up? Less energy, and so everything's quantized, so it's going to be shorter, longer wavelength that does that. The more conjugation, the smaller the gap between your HOMO and LUMO. Things that are highly conjugated, that gap gets even smaller and smaller. Your absorbance starts moving to the right to longer wavelength. Why is beta carotene orange? You already said it, huh?
It absorbs one wavelength and therefore reflects the other.
Yeah, it absorbs, that's really what it's reflecting, right? Now, let's go back here before we look here. What's this lambda max?
440.
440? Now, we don't have the colors. I think this is the only place I should color. So where's 440 at here? 440 is probably about right here. So what color is this? Sort of blue. The orange actually absorbs blue, I think. 440. But what happens if you take blue out of white light? I think it'll look orange. Okay, where's orange at on here? If we go red, orange, isn't orange more like here? It's not absorbing 700. Well, you can look at the color wheel. And the color will be on the opposite side. Beta carotene absorbs 440, that's its main absorbance. This is black and white, yeah. That's what it absorbs. The color you get is on the other side. This is what you get. What do you get? You get what it reflects, and it reflects orange. Okay, types of questions you'll see here. Rank these three in order from highest to lowest lambda max. Which one will have the highest lambda max? That's 1. Why is that 1? Why are we going to have the highest? Most conjugation. Okay, what's going to be the next? 2, 3. Why is 2 higher than 3? Because in 2 and 3 both have 2 double bonds. But what's the difference? In compound 2, they're conjugated. And so you have a conjugated system. And it's that increased conjugation that moves your absorbance to the right or narrows your HOMO-LUMO gap. Does that 1, 2, 3 make sense? Here's some compounds we may have seen before. You made the dibromide from the double bond, stilbene dibromide. Which one have the highest lambda max? These are pretty straightforward. I see my green. See, stilbene has, all this is conjugated through here. But when we brominate, we remove the pi bond, these 2 carbons are now sp3. You've got a conjugated ring, but they're not conjugated with each other. So bromination decreases the conjugation. So which will have the highest lambda max? Stilbene. Okay. Which one of these is more likely to be colored? The one with the higher lambda max, the one that's more towards the visible. Yeah. This is typically pretty much pure white. If you remember it, you made it in the lab, it's almost like snow white. Now this is pretty much white, but if you put these beside each other, this has a very pale yellow color probably. Very pale yellow. Does it make sense that it's very pale yellow as opposed to very pale blue? Go back to the I don't have actual UV vis of these, but look at we're absorbing in the ultraviolet, what if this kind of did something like this? And this is 400. What is it absorbing right here if it's a little bit into the visible? What color would it start absorbing at 400? Violet. What's the opposite side of violet on the color wheel? Well, where's 400? If it starts absorbing here, you're going to get over here. Now again, it's a black and white, but I bet that's probably going to be yellow. As you barely start moving into the visible and absorb that blue-violet color, the complementary, I think it's called color, is going to be yellow. So that's why compounds are white, and they start moving towards yellow. And the yellow can become deeper and deeper as there's more and more absorbance. That's why your initial colors and thus your common colors are not like red and green. Because you really have to move to the right to get those colors. How do we visualize TLC usually? What type of light do we use? UV. UV? Yeah. I'm not going to try to explain that, but your compound does need to be UV active to be able to be seen under UV light. But there is also a dye on the plate. But just remember, you're using a UV light when you look at your TLC spots. I'll just show you this. This is just one more time. I'm not going to try to erase, guys. The board is back to being ugly. This is just showing again that as your ethylene or ethene, as you increase in conjugation, add more conjugation, what happens to your gap? The gap between the HOMO and LUMO gets smaller and smaller, and so it's easier to excite, thus you need longer wavelength to do it. Let's look at a couple of applications. You probably saw some color indicators in Gen Chem, right? Gen Chem lab? I don't know the name of this indicator, but this is a colorless form. Apparently under an acid it's colorless, but if you add base, it turns into this form, and this form is magenta. What color is magenta? Kind of violet, purplish, or something like that. Remember Magenta on Blue's Clues? Magenta's coming over. Does it make sense based on structure that this could be colorless, but that's going to be magenta? So this is colored, so which one's absorbing more in the visible? This one. So would you expect this to be more conjugated or less?
More.
More. Look at the structure. Does it look more conjugated than over here? Over here you have 3 benzene rings, but does that carbon there have a p orbital? No. So 3 individual benzene rings. 3 different systems. But when this opens up, and actually one of these phenol groups moves in, electrons move in, you could show mechanism for this. Base does that. Base is hydroxide. What do bases do? Take H's, this becomes minus. Then the minus you can move electrons in, electrons in, electrons in, kick off that oxygen. Now that goes a little bit against what we've said. That oxygen doesn't look like a good leaving group unless it's protonated. But actually it's resonance stabilized when it gets kicked off. That's a carboxylate. But in this form, there's a p orbital here. And you got p orbitals all through here. And now you have just all these p orbitals overlapping instead of 6, 6, and 6. And this becomes colored. If you add acid, well, this protonates, and then this adds back, and the electrons come back this way, get back over here. So basically, whenever you're doing an indicator, you've got some chemistry going on, and your indicator's changing forms from a colorless form to a colored form. The colored form is usually highly conjugated. We can also sort of go backwards. We can study conjugation because usually we draw structures on the board and we say, hey, it looks conjugated, but is it really? Look at these two examples. These two compounds are isomers. Yikes. That's a trans double bond, and this is a cis double bond. You can see it there on the paper. Trans and cis, yeah? Lambda max for this has been determined to be 300 nanometers. This one's 280. Why is it lower? Does it have less conjugation or more, or what? Less based on what? Very good. What does this number tell you? It has more or less conjugation?
Less.
Right. A number tells you it has less conjugation. Well, why? I mean, I see p orbitals, p orbitals, p orbitals. Why does this have less conjugation? That's what the number's telling us. We trust the number and what it means. Why does it have less conjugation? One thing you have to keep in mind, just because p orbitals are next door to each other don't mean they're conjugated. There's 5 p orbitals next to each other, if you can see that. Are they all 5 conjugated? No, I got 3 conjugated and I got 2 over here. These are not conjugated. Okay? What's going on here is there's an H here. Okay? What is happening here between that H and that oxygen? They're clashing. Because they're clashing, what happens? They avoid each other. See, all this has to be planar. For it all to be conjugated, that's p orbitals all the way around. Okay? 6 here, 2 here. They're all like this. But when these avoid each other, what happens? Think. Okay? And the conjugation is sort of disrupted. It's only partially overlapping. We get into that gray area. And the lambda max is not as high. So we can use UV-Vis to tell us about the actual conjugation. Of course, you can also do some molecular modeling here, and you can see how the molecule may be bent, or it's not all planar, and it's like this a little bit. Okay. Let's see what else is here. Here's a couple of actual spectra. UV-Vis. These were done on a nice instrument where you could sort of overlay plots. This is a compound we used to do at Georgia State in the Organic 2 lab. The chalcone compound is converted to the epoxide using MCPBA. We know that reagent, right? Okay, here's the 2 UV-Vis sort of overlaid. Which one has a higher lambda max? Well, here's the epoxide. It's about what, 240, 250? And and then it tails off. Here's the chalcone. It's moved to the right, and its major absorbance, lambda max, is more like close to 300. Does that make sense that the chalcone would have a higher lambda max?
Yes.
Yeah. Once you make the epoxide, the two carbons there are now sp3, and it's no longer conjugated all the way through there. Now, this really doesn't show. Which one of the two compounds is, one of them is pure white. The other one is slightly yellow. If you just glanced at it, you'd call it white, but it's got a little, tiny yellow tint. Which one is probably pure white? Epoxide. Yeah, the chalcone is actually a tinge yellow. Now, this doesn't show it here. Maybe the sensitivity or the concentration. So it looks like there's no absorbance into the visible. Also, where exactly is visible? Some people say 400. One of the handouts said 380. But this may actually be more like this. And you get a little bit of visible absorbance, just a touch, absorbing that violet light and make it be a little bit yellow. And of course, if you extended the conjugation more, you could move it so it's here and it's like truly yellow, and maybe even deep yellow. But yeah, epoxide is pure white. What happened to the last sheet? Did we have some sunglasses?
Yeah.
Can I show that? There's another application. Anybody know the transition lenses? You go outside and they darken. Why does that work? Well, you can read this, but it's something to do with UV vis. The lenses have these compounds in them, and this one looks highly conjugated compared to this one. And somehow when you go outside, it converts to this form, and it starts absorbing differently. You'd have to read it. I haven't read it in a few years. But there's actually compounds in the lenses, and chemistry takes place between these two forms, almost like an indicator. But one absorbs differently than the other because one has more conjugation. You can read it and see about it. Isn't it amazing to have chemistry going on right there? Molecules. But how do people develop this technology and get materials, forms and stuff? You know, taking stuff we do in flasks, making compounds, but then you got to turn it into an application, materials science type stuff, technology, etc. You can read some of that. In the end, sort of the take-home with UV vis is conjugation increases your lambda max. Okay. Understanding why, and then a couple of little applications we showed. Any questions about UV vis? In the labs, Organic 1 and 2 that I teach, I don't do a UV vis experiment. I've sort of wished I would develop one, maybe make a product and then do a UV vis, but currently I don't do it. Did y'all do UV vis in Gen Chem? No? You get a lambda max. It's not highly, unless you're doing something very specialized where it can, the information that UV gives you is highly important. Well, of course it's important, but the day-to-day organic stuff, IR and NMR, is just more important. It's a physical constant. It's sort of analogous to, remember when we did index of refraction or something? We got that sort of just number. Although there is more applications to UV vis, I think, than just a simple UV refraction number. Or not UV refraction, but refractive index. But of course, if you're doing optics or something, then refractive index may become very important. But why is the wall blue? Hopefully you now have can maybe answer that. There's some molecule up there on that wall that's absorbing some visible light and reflecting blue. It's absorbing, what's it absorbing? Opposite of it, yeah. It's probably absorbing yellow. So if it's absorbing yellow, which is what nanometer? It's more towards 800. That's like 700 probably. Red, orange, yellow. 600, 700. So is that slightly conjugated or probably highly conjugated? Yeah, there's some molecule that's probably highly conjugated. And a lot of times if you look at molecules that are called dyes, they don't have lots of pi bonds. I mean, beta-carotene to me looks like a dye. Maybe you see dyes, they have lots of alkenes, lots of conjugation. See some green compounds, those things, highly conjugated. Any questions about UV vis? There will be UV vis on the test in a week from today. Again, pretty simple take-home conjugation. Anything else, guys? Last questions? Got 5 more minutes. I do have a lab for my guys to pass back. Those are all their notebook pages. We'll do that now. Y'all have a good holiday and be safe and don't study too much. Make sure you take a break, get some